General relativity and quantum mechanics have survived a century of rigorous testing, yet they operate on contradictory sets of rules. General relativity treats space-time and gravity as a smooth, continuous, and strictly classical entity, where certainty is absolute. Quantum theory demands physical observables obey rigid limits on how accurately they can be measured simultaneously, a boundary defined by Werner Heisenberg's uncertainty principle. To test if these two frameworks can be unified without building impossible Planck-scale particle colliders, physicists have developed a tabletop experimental framework called gravitationally entangled entanglement, or GIE. The logic is absolute. Entanglement is a purely quantum phenomenon. If the gravitational field can act as the sole mediator to entangle two particles, the gravitational field itself must possess intrinsically quantum degrees of freedom. The original 2017 GIE proposals required taking two distinct massive particles and placing both of them in a state of quantum superposition simultaneously, an immense operational hurdle. A 2026 paper from researchers at Oxford's Clarendon Laboratory offers a way to lower this barrier. Their calculation demonstrates that verifying quantum gravity requires only a single mass to be placed in a spatial superposition. By coupling this single superposed mass with specific measurement techniques, a secondary probe particle will experience an effective negative momentum transfer. Because classical gravity is strictly attractive, observing any kind of repulsive gravitational effect serves as a definitive singular witness that spacetime operates under quantum rules. The setup relies on a Mach-Sender interferometer. A source mass enters the apparatus. At time t0, it's forced into a spatial superposition, occupying two paths, xa and xb, simultaneously. Along the side sits a secondary probe particle, prepared with high momentum uncertainty, depicted as a broad spatial wave packet. Both particles are maintained in free fall, or secured within a trap that fixes their y and z coordinates, confining the interaction to a single axis. Because the source mass exists in a spatial superposition, the probe particle is now exposed to a gravitational field originating from two different locations at once. Over an interaction period from t0 to time t, the two particles influence each other purely through mutual gravitational attraction. If gravity follows quantum rules, the probe particle feels the pull of two distinct attractive gravitational vectors, one from the source's position at xa and the other from xb. The probe's physical position remains largely fixed due to its massive initial momentum uncertainty. However, its momentum wave function is permanently altered by the interaction. Because the probe responds to a superposition of two different physical massives, the gravitational field links their properties, creating entanglement between source and probe. The probe's quantum state now encodes a superposition of two different attractive momentum transfers. As the source mass exits the interferometer, the experiment employs a measurement technique called post-selection. The researchers discard the majority of the data, only retaining the exact runs where the source particle collapses into one highly specific predetermined quantum state. This momentum chart shows the probe's wave functions. The blue and yellow curves sit on the positive side, reflecting attractive gravity. Due to post-selection, they undergo destructive interference. The yellow subtracts from the blue, generating the green curve, shifting the probe's average momentum into the negative domain. This outcome arises from a quantum interference of force, where two distinct positive attractions mathematically combine into a net repulsive push. The baseline gravitational attraction between two microscopic particles is infinitesimally small, placing it near the limit of what modern instruments can reliably measure. To make this repulsive force detectable, the researchers calculate the interaction using a mathematical framework known as weak value amplification. By selecting an initial source state and a post-selected source state that are almost entirely orthogonal to one another, the framework generates a massive amplification factor. The effective negative momentum transfer applied to the probe is multiplied by a factor of hundreds or thousands, pushing the anomaly past the threshold of modern laboratory detection capabilities. Translating this math into physical reality starts with the primary source mass, which could be a microscopic nanodiamond suspended in a controlled magnetic trap. The diamond contains a single nitrogen vacancy center. By applying inhomogeneous magnetic fields to this specific defect, experimenters can manipulate the particle's spin state and force the entire mass into the necessary spatial superposition. For the secondary probe, the researchers propose using an ensemble, specifically a Bose-Einstein condensate of cesium atoms, allowing them to measure the final momentum distribution of many particles simultaneously. An alternative approach utilizes a heavier mass, around 10 to the negative 20 kilograms, for the probe. This simplifies the setup, as the heavier probe particle does not need to be placed in a spatial superposition itself. The required distances are in micrometers, the mass scales are mesoscopic, and precise magnetic traps already exist. The required hardware falls within the developmental trajectory of modern tabletop physics. There is a direct statistical cost to the weak value amplification. The higher the amplification factor engineered into the system, the lower the probability of the required post-selection actually occurring. If the experiment is tuned to amplify the effect 1,000 times, the probability of the source mass collapsing into the correct state drops below 0.1%. The apparatus must process a large ensemble of repeated runs to detect the momentum shift. But running an automated experiment thousands of times is more practical than the physical difficulty of preventing decoherence in two separate massive superposed particles. Furthermore, the experiment bypasses the need to measure direct quantum correlations between the particles, removing a major hurdle in quantum gravity testing. A classical gravitational field can never generate a repulsive force through interference. Measuring this anomalous momentum transfer will definitively witness the quantum nature of gravity.